welcome to the Rustlang conference for 2023. My name is Boiko and I work as a specialist solutions architect at AWS. And essentially today I'm going to talk a little bit about Rust and why I think it is the best fit for writing your serverless workloads and especially lambda functions. To be honest, when I started looking at Rust and learning it a year ago, I was something a little bit skeptical about that. Yeah, I would use Rust as my primary language for writing lambda functions. But over time, I came to the conclusion that, yeah, Rust is the best fit for writing the lambda functions, especially given how lambda runtime runs your code. So let's get started and look at today's agenda. First of all, I will remind you a little bit about lambda, what it does and how it runs your code, and give a short overview. And then we will look at how you can kickstart your new project and run and create your lambda functions and what tools and options are there. Then we will be talking a little bit about lambda extensions. This is another way where you can apply Rust and it perfectly fits there as well. And we will look at how to write a lambda extension with Rust. And then, yeah, we will cover all and summarize all the things that we will be looking at today. So let's first talk a little bit about lambda and how it runs your code. Essentially, from the developer standpoint, you can think of lambda as another compute option, which, given a code written in many different languages, it just provides compute runtimes, compute resources to run that code. And essentially then you write code and that code interacts with different underlying resources such as AWS services, databases, or any other resources. And lambda essentially allows you to react to different incoming events from other AWS services or external APIs. And as you see, you can use different languages. Probably you can't see Rust here because in lambda we have different types of languages. We have so-called provided runtimes, which provide some environment for you for Python, JavaScript, Java. Or you can use so-called bring your own runtimes, where you can create a custom runtime and execute that runtime and run any language whatever you want. With Rust, it is usually a custom runtime, but don't think that you will spend a lot of time creating all these primitives yourself. I will explain in the future that you don't need to care a lot about this. But if we look at bigger picture, you have your code, then probably you will need to provide some configuration options, referring maybe to some external resources or some configuration parameters. Then, of course, because your lambda function needs to react to different events, you will need to configure either event source mapping or provide a way how your lambda function will receive those events from the external sources. And there are different things which allows you to version your lambda functions, to use different deployment strategies, etc. But I'm not going to focus a lot on this aspect. And of course, security is a very important thing, and you need to think what resources are available for your lambda functions, or who, on the other hand, can run and execute your lambda functions. And this is clearly defined and protected by assigning appropriate IAM and lambda permissions and using execution roles on the lambda functions. And in the end, once you write a code, there are two different options how you can package the code and deploy it in the lambda runtime. The most commonly used packaging is zip archives. So you can package all the things as a zip archive and deploy it into a lambda runtime. Or you can also use container images. For example, if you already built some pipelines around producing containers and container images, then you can probably adopt and reuse them to produce also images for lambda functions. In terms of Rust, in the end, you will have a binary, and then this binary you can package both as a zip or as a container image. There are some differences, and usually I encourage you starting with zip because it is easier to implement and to deploy, unless you have some specific requirements where you want and need to use container images. Another very important thing, especially in terms of Rust, is how you can configure how much resources are in terms of hardware are available to your lambda functions. And if you look at the configuration options, you will see that there are not plenty of options here. And essentially, the only option you can configure is the amount of memory given to the lambda to your lambda function. But interestingly enough, the amount of memory you give to your lambda function also tells how much lambda runtime will give CPU cycles to that to this or that function. And this CPU capacity is allocated proportionally to the amount of memory. So the bigger amount of memory you give to the function, the maximum is 10 gigs here. The bigger number of CPU cycles your function will get. And essentially, if you think about virtual CPUs, if you give your function around 180 megs of memory, it will transform into one full vCPU. And it will scale up to 6 virtual CPUs if you give the maximum amount of 10 gigs to your lambda function. That essentially means that that function will be assigned 6 full virtual CPUs. And here comes another very important aspect, is the pricing. And the pricing for your lambda functions consists of two options, of two things. The first one is the number of requests. So the more requests you assign and the more requests you issue to the lambda function, the more you will pay. And another dimension is the duration. And duration is calculated in gigabytes per second. So it is essentially the amount of memory you give and configured for this particular function and the time your function is running. So essentially that means the more memory you assign to a lambda function and the longer this function is running, the more you will pay. But the duration is measured in 1 millisecond, so it is quite granular. If you can optimize the time of how long your lambda function is running, it essentially means that you can optimize also on the cost. And another very important thing to realize here is that you will pay the same for the function which runs 100 milliseconds with 2 gigs of RAM configured, or the function if it runs for 200 milliseconds with 1 gig of RAM configured. But what if you can minimize both things? So you can have less memory configured and your function runs less amount of time. So it essentially means that you will pay less. And here Rust comes into play because, again, it is super fast and super optimized, and it essentially allows you to run your functions faster in terms of time, and in many cases it also can run in a less memory and less CPU, because again it is quite optimized, and essentially that will imply that your functions will cost you less. So let's talk a little bit about Rust's performance and cost characteristics applied to serverless workloads and to Lambda functions. First of all, there are different tests run by different people. Probably one of the most well-known is this test of Hello World application. Essentially, it is not super real world scenario, but it can give you a high-level view on different runtimes and the amount of time it will take to run these simple workloads. But again, in real life, probably we won't be running Hello World applications often. There are a lot of data and a lot of people already compared different runtimes, Python versus Rust, like in this example, or Node.js and TypeScript versus Rust. And essentially, in many cases, we observe that customers who adopt Rust compared to any other runtimes on Lambda, they observe both. They can see the performance gains, and usually those performance gains applied to how Lambda bill you also convert into the price and cost gains. And essentially, if you look at the cost efficiency, there are a lot of samples. For example, one of our customers, they see that the reduction of amount of CPU and memory used in production dropped significantly. And essentially, yeah, it is good in terms of performance, but if you look at Lambda, as I explained, it is also means you pay less. Another great example, I have a customer who was running the majority of their workloads in Node.js, and essentially they were quite happy, but then they realized that there are certain types of workloads that require lower latency, and they started to optimize on the latency and started evaluating different options. And in the end, they came to the conclusion that essentially they rebuilt some of their applications in Rust, and they observed, first of all, the lower memory usage for their functions. So the same function running on, for example, Node runtime and in Rust required different memory configurations, and they could get the same or even better performance at a lower memory configurations for their Lambda functions running in Rust compared to Node or Go runtimes. And essentially, because the memory is less, the speed is better, they also observed some cost gains as well. So this is a quite common pattern. You may ask, does it mean that I should rewrite all my Lambda functions in Rust immediately? Of course not. Of course, it will take time and effort to teach your teams Rust and rewrite everything in Rust. Probably even you don't need to do that. immediately. I have another quite interesting customer example that the team was primarily using Node.js for their serverless application, and essentially the serverless application consisted of 100 of different functions, but they identified 2 or 3 hot functions that essentially almost every request coming into their system hit those 2 or 3 lambda functions. And essentially they decided that, yeah, we want to optimize those functions. We want to minimize the latency. We want to make those functions the most performant ones. And essentially they started rewriting only those 3 functions in Rust, and they are already observed quite great impacts in terms of performance. First, because those functions were hot, and as I mentioned, all requests coming into the system had to pass through those functions. And also they observed some cost gains, because again, those functions were most called the majority of time, and reducing the cost was also a great benefit. But they happily stay with Node.js on all other functions, and they still haven't rewritten the whole application in Rust. So usually this is the best strategy if you already invested a lot in your serverless applications and you already run in different runtimes. Identify the most important, the most critical parts of your application and probably rewrite those in Rust. And it is quite obvious. Another very important thing about Rust is sustainability. Again, because you use less compute resources, you can use it more efficiently. And in the end, with serverless, it is already quite sustainable, because again, you don't have to run those resources 24/7. Serverless automatically scales up and down depending on your workload. But again, applying Rust to serverless will make you even more sustainable. And again, Rust is heavily used under the hood by different parts of AWS. And for example, if we look at Lambda, under the hood, Lambda is using Firecracker VMs to isolate your workloads. And those Firecracker VMs, they're written completely in Rust. So already, even if you don't use Rust as your language to implement Lambda functions, under the hood, Lambda will already use Rust, and it is will already be beneficial in terms of sustainability. But how you can start? For example, you know Rust, but you want to run some and create some functions in Rust. How you can do that? I personally recommend you looking into a tool called Cargo Lambda. It is an extension for our Cargo tool. And essentially it provides you with a set of workflows which allow you to bootstrap a new application, to test that application locally, to deploy it to your test AWS account, to build that application. Again, it supports, for example, cross-compilation, and for example, you can target different Lambda runtimes, because In Lambda, we have two different CPU options. You can run your functions in x86 or an ARM architecture. So, and with Cargo Lambda, you can easily build for both of those architectures. Again, here you can find a link to the Cargo Lambda. So if you scan this QR code, it will navigate you to the site, and there you will have quite great documentation how to use this tool. Another thing which I personally like around Cargo Lambda is that it is agnostic to infrastructure as code tools. So you may use this Cargo Lambda with different infrastructure as code tools. For example, if you use Terraform, or if you use SAM, or if you use CDK, you can integrate them with Cargo Lambda. Then, once you bootstrapped your application, let's look at some sample application, and I will guide you quickly through how typical small serverless application written in Rust may look like. So this is a small application consisting of API gateway for receiving incoming HTTP requests. Then we have a lambda function where we implement some business logic, and, for example, quite common use case to have a DynamoDB as a data storage. We have quite good documentation how to build and how to use lambda functions with Rust. Again, you can follow this link on the page and get quite comprehensive tutorial and guide how to build and how to use Rust with lambda functions. Let's briefly look at main themes in this sample project. First of all, as you see, we input number of libraries, and essentially there are two important libraries. First is lambda HTTP, and essentially, remember I mentioned that if you want to use Rust on lambda, you need to create your custom runtime. And essentially, if you need to create a custom runtime, that custom runtime is responsible how your code is interacting with lambda. And there are certain specifications you need to follow, how you can get the events from lambda runtime, how you should pass the responses back. And yeah, you can implement that yourself, but we already done it for you, and we have this Rust runtime for AWS Lambda. It's an open source project, and it encapsulates all the interactions between your code and a Lambda runtime. And essentially, it also adds a lot of syntactic sugar. For example, if your Lambda function consumes and gets events from API gateway, there's another abstraction on top of Lambda Rust runtime, which encapsulates how those HTTP events are coming into the Lambda function and how you can interact with them. And another important input here is DynamoDB interaction, and for that we are using AWS SDK for Rust, and it essentially allows you to interact with Dynamo or any other AWS services. Then the most important function in your code will be a function handler, and essentially this handler function is the main function where you can write and put the code. And for example, in this example, it gets the event, and this event abstracts the data which is coming from API gateway or any other HTTP sources. And in the end, your function should return a result type. And if you successfully complete the function, you should return OK and some response from your lambda function. Then within the handler, it's an arbitrary Rust code. You can again write some basic things in the handler function, but in reality, if you have more sophisticated business logic, you will put that logic in separate Rust functions, methods outside the handler function, and you can essentially interact and call them for sure. And another thing is that you can do within a handler function, you can interact with lambda environment. For example, you can use println or tracing mechanism to emit logs for CloudWatch. For sure, you can interact with local TMP file system. It's an ephemeral file system available for the lambda function during runtime of this or that function lifecycle. And of course, you can make any network calls to external resources, to any other AWS services. Another thing you should add into your lambda function is a main function. And essentially, this is the entry point which will be called by a lambda runtime on the start of those runtime. And here, the only thing you should be aware of this is an asynchronous invocation, and we use Tokyo for that. So you must annotate the main function with Tokyo main and make it a synchronous invocation. Another very important thing is that because this main function is called during the initialization of your lambda runtime, you can declare some independent resources which will be reused by your handler function. Usually you can define some external dependencies, creating an SDK client or getting the configuration options for the function. And then those configuration options and those SDK clients, they will be preserved in memory, and your handler function doesn't need to reinitiate and recreate all that shared resources for the subsequent calls. And essentially, this is a best practice how you should initialize some common resources which will be reused in your handler function. And then, as I already mentioned, OK statement in your handler function just ends the execution, and usually you return a JSON document. If it's a synchronous invocation, or if it's asynchronous, for example, then you can return something, but you can also return empty OK response, because essentially for asynchronous invocations, lambda runtime won't forward any data back to the caller. This is a quite good thing, and you can build your business logic with lambda functions. But another quite interesting application for Rust and in terms of lambda and serverless is so-called lambda extensions. First of all, let me briefly describe what lambda extensions are. It is additional process which runs alongside you with your main function and your main code. And it essentially allows you to capture some diagnostic information, maybe run some instrumentation for the main code, fetch some configuration settings out of external parameter stores, or react to some function activity, maybe imposing some additional security guardrails into your Lambda functions. And essentially, in terms of extensions, there are two different types, but for today's talk, we will be focusing more on external extensions. And external extensions, it's like a separate process that runs in the same runtime, in the same execution environment. And usually you can query different parameters from your Lambda runtime, or you can again use this separate process for monitoring, observability, and security. One important thing here is that this external extension, it still shares the same runtime environment, and essentially that means that it shares the resources like memory, CPU, and all other things. And another very important thing is that your extension doesn't have to be written in the same language as your main Lambda function. So that essentially means that you can create extensions in Rust and augment the behavior of Lambda functions written in Node.js, in Python, in Java, or any other languages. But here, important thing that, those extensions, they can impact the performance of the main function because the resources are shared. And here where Rust comes into play, because again, it is the most performant language, and essentially now I see a lot of extensions are being created with Rust. So it is a perfect fit if you want to augment the behavior of the function and you want to create an extension. Rust is a great option here. Again, if you use Cargo Lambda extension, you can easily bootstrap a new Lambda extension. And essentially here you see that there's another method which you need to implement. It is event extension method. And it gets the Lambda events, and then depending on what happens with your Lambda runtime, you can interact with the main code, and you can react when the Lambda is being invoked, Lambda function is being invoked, then you can react to those invoke events. Or when the Lambda runtime is being shut down, so you can again do some maintains, clearance, or emitting some logs, or doing some other things. And then you have this main function as well, and essentially this main function just passes and executes this events extension function. So here I encourage you looking at extensions. There are pretty good samples what you can do with Lambda extensions. Probably one of the most well-known ones is Lambda adapter. And essentially it was created by one of my colleagues, and this Lambda adapter allows you to get API gateway HTTP events and transform them back to actual HTTP calls, so that, for example, if you want to run in your Lambda functions some legacy applications written in traditional frameworks like Express.js, like Flask, like PHP, for example, you can take that application and you don't have to change anything. So this application will still listen on a particular port, but you can't expose a port with Lambda function directly. This adapter, written in Rust in the form of extension, essentially it calls, makes a call to a port which your application listening inside Lambda runtime, get the response and transform that response back to actual JSON payload understood by API gateway, for example. So a nice example what you can achieve with Rust and Lambda extensions. So in summary, Rust is the best fit for Lambda functions, and it essentially allows you to get the best cost performance characteristics. So I highly encourage you, if you want to use Rust with Lambda, go and experiment. And essentially with Rust you can both build business logic in terms of normal Lambda functions, or you can also use Rust to create different Lambda extensions and to extend capabilities of your Lambda functions, even if the business logic is still running and executed in other languages. And there are a lot of tools, not only Cargo Lambda, we have support for Rust in SAM, so you can start using and start building with those tools quite easily new projects. With that, thank you very much. Hopefully I encouraged you enough to try build some Lambda functions with Rust. In case you will have any questions and want to communicate, feel free to reach out and ping me on Twitter. With that, thank you very much and hope you enjoy this conference.